everyone. Welcome to the Modern Application Architecture Best Practices Summit. Today's event was organized by the hardworking folks at two 1105 Media publications, Redmond Magazine and Virtualization and Cloud Review, who have brought together some of the best independent experts on today's topic. Many thanks to our sponsor, Red Hat, the world's leading provider of enterprise open source solutions. They've been innovating in that space since they were founded in 1993 by Mark Ewing, who was well known for wearing his red Cornell University lacrosse hat given to him by his grandfather, thus the name. They currently contribute to 450 open source projects, and they continue to evolve their community-powered approach to deliver Linux, hybrid cloud, edge, and Kubernetes technologies. Many, many thanks for making this event possible. And thanks to you for joining us. I'm John K. Waters, Editor-in-Chief in the Converge 360 group of 1105 Media, and I'll be your moderator for the first of three information-packed sessions. Before we get started, a bit of housekeeping. Each of today's sessions is being recorded for later access. Keep an eye out for an email with a link to that recording. It'll be coming your way in the next few days. Each of today's sessions will be followed by a 5 to 10 minute Q&A. You can type your questions into the Q&A box at any time. We'll do our best to get to all of them. Our sponsor has provided some extra resources that you won't want to miss. They're available now on your console. At the end of this summit, you'll be asked to take a short survey. We know you guys are busy, but we're hoping you'll take a moment to give us some honest feedback about today's event. And last but not least, at the end of the third session, one lucky attendee will be receiving a DJI Mavic Air 2 drone, the next big thing in aerial content creation that combines high-end imaging features and powerful flight performance in a compact form factor. But you must be present to win, so stick with us. Now let's get started with our first session, Application Architecture Best Practices. For this session, we called on technologist, creator of compelling content, and senior resultant, Howard M. Cohen. During his 40-plus years in the IT industry, Howard has held senior executive positions in many of the top channel partner organizations, and he currently writes for and about IT and the IT channel. Howard is a sought-after speaker, an insightful observer of the technology landscape, and a popular columnist for application development trends, my favorite 1105 Media publication. He's one of our favorite speakers, and I know you guys are in for an awesome session. Take it away, Howard.
Thank you, John. I like application development trends, too. It's one of my favorites, too. Speaking of application development, today's topic is application architecture best practices. Those of you who've been at any of my presentations in the past know that I always like to start with a word of the day. It's, I guess it's the writer in me. Today's word is one of my favorite words, actually, and that is design. Not this design in particular, but design in general. People thinking about how things look and how we experience them. It's often mistaken, it's often confused with architecture. Design and architecture are not the same thing. Architecture describes the underlying structure that keeps the thing up and running and supported. Design really describes the experience of using it. Another opinion on that difference comes from one of the 17, count them, 17 authors of the famed Agile Manifesto, Martin Fowler, who said that in most successful software projects, the expert developers working on that project have a shared understanding of the system design. This shared understanding is called architecture. That's a little bit oblique, but yeah, I'll go for it. So let's get down to some definitions. Actually, you know what? Before we get to the definitions, let's launch our first best practice of the day. First and foremost, best practice in application architecture is to carefully select which type of architecture you're actually going to use, or which type of architectures you're going to use on various components of the project. So selection is number one, and not surprising, selection is often number one in a lot of places. So now, these definitions, starting with the definition of application architecture, just for clarity. It's a framework, right? So you're using various different programming patterns, various software development techniques, obeying certain principles of how logic works, and basically following guidelines that determine how your software will be created, developed, tested, deployed, and maintained. That was a mouthful. It also describes the interactions between the various components of your software construct. There's middleware in there. There's application programming interfaces in there. You're using databases and indices for those databases. There are various components, and the architecture describes how those various components work with each other. It assures that those components are each isolated so that we can deal with each one individually, but we also know which ones depend on which other ones. Now, just to get a little clearer about dependencies, in programming, dependencies can be either tightly coupled or loosely coupled. When they're tightly coupled, that means if one fails, it's going to take others. They're going to fail too. When it's loosely coupled, it's much more tolerant. Things can fail and other things will just keep on going. You'll hear examples of each as we move through the different architectures that we're talking about today. It also describes your environmental requirements for performance and for scalability. Scalability, of course, being the ability to match the growth of your company with the growth of your application. And then, of course, it also talks about how everything talks to each other. How do they communicate with each other? And how does the data flow through the system? What is the workflow, if you will, the data flow through the system? Basically, and it's a good rule of thumb, a good software architecture is necessary. If you want it to be scalable, if you want the system to be maintainable, resilient, reliable, you really need to adhere to a given architecture consistently across every member of the team and every component of the software. Okay, so now we have a better idea of what application architecture is. Let's start to examine some different types of architecture, starting with a more general category, if you will, which is N-tier architecture. Those of you who've been in IT for any amount of time know that everybody loves layers. There's layered security. There's the ISO OSI 7-layered network model. Layers, layers, layers. Well, we have layers here too in application architecture. As a matter of fact, N-tier architectures are the most common of architectures. Fundamentally, the system is organized in layers that lay on top of each other and communicate with each other. And they look something like this. There's a presentation layer. Now, that happens to be the top layer of the ISO OSI internetworking model, too. Why? Well, because they're both closest to the user. The presentation layer is what the user gets to see and gets to work with. So there's various different ways of building that presentation, but that's your connection to the user. That presentation connects to various services that make things happen within the presentation, and those services depend upon the business logic that's driving the functioning of the application. All of this depends upon a data layer. There's got to be data, or if you're going to have data processing, there's got to be data to process. So there is a data layer, and then that all leads down to the persistence layer, which is basically what keeps everything working. So the first of our specific architectures is the monolithic architecture. And for those of you who have not seen Stanley Kubrick's 2001: A Space Odyssey, you are required to go home after this session and look it up on Netflix and go watch it, because it's a great movie. And this monolith is featured in that movie, a great big block. And indeed, that's exactly what monolithic architecture is about. Most legacy systems, in matter of fact, probably all legacy systems, are written in a monolithic style. In a monolithic style, everything the software does, every function, every subroutine, everything all the logic, it's all built into that one big block of code. All in there. Now, the thing about having one big block of code is that the dependencies are very, very tightly coupled. If one thing goes wrong in a monolithic program, it has the ability to bring down everything. So if you have hundreds of users depending on this monolithic application and anything goes wrong, they may all be sitting there twiddling their thumbs for a considerable amount of time, because recovering from that is very complex. The nature of such a big block of code, any big block of code like that, is going to be complex. And to fix it, you're going to have to first find the problem, figure out how to fix the problem, make the programming changes required to fix it, then you have to test it, and finally you have to recompile it before you can re-execute it and get everybody back up and running. That's a lot of time. It's a tremendous amount of time, which is what drove the creation and development of the other architectures that we're going to look at today. Also, monolithic architectures just don't scale well. Often they are limited in the number of users they can accommodate. And to add more users, you've got to basically go back to the drawing board and figure out what you're going to do. That also, they're very difficult to update. Basically, updating usually involves reloading the entire executable, which can be very, very time consuming. So that's the original. That's monolithic architecture. That's how we've all been programming since forever, since IBM rolled out the System 360 a million years ago. Next up, we got to service-oriented architecture. The service-oriented architectures arose basically in the 1990s, and they've developed over the last 30 years and evolved into what we today call microservices. Now, since microservices basically have the same fundamental structure as service-oriented architectures, let's just save a little bit of time and go right to microservices architecture, mainly because it is becoming, and probably is now, the most popular software application architecture in the world. Basically, everything kind of looks like this. Yes, involved in some microservice. Each application, the overall application that used to reside in that one big monolithic block of code, is now broken down so that each thing that was done in that block of code, each function that was performed, each subroutine, each logic equation, everything that was done in that block of code exists now as individual instructions, little pieces of service that are independent. And they are basically put into a container along with all the resources they need to run. Runtime libraries, location of various storage and other resources. They're ready to rock. And they need to be called upon, and when they're called upon, they get out there and they do their thing. So these services can communicate with each other. Each individual service may work in conjunction with other services, and they're all basically connected through a common enterprise service bus. But the concept is that when queued, a microservice is instantiated right then and there. It's created. It's put into its container along with its resource, packaged up, and ready to get sent on its way. Before it gets sent on its way, it is double-checked to make sure that it is properly constructed and fully functional. If it fails that test, it's discarded instantly. It never gets out there where all the other microservices are doing their thing. It is killed off and reinstantiated. So another copy is made, again tested, and this time it worked. It's fine. Here we go. And it's sent out into the cloud to do its job. So what does that mean? That means that microservices, by their nature, are very resilient. They're very loosely coupled. And if one happens to be faulty, nobody will ever know it because it doesn't get past that first test to make sure that it's constructed properly. So again, microservices, extremely, extremely resilient, can easily be transported to wherever they're needed. And because they work so well in a cloud environment, they are now commonly referred to as being cloud native. So when you hear somebody talk about cloud native software, you know now that they're talking about microservices that are packaged in containers, microservices in containers. That structure also lends itself well to DevOps processes and so forth. So you're going to see this just grow and grow. Next, there are event-driven architectures. And I've written fairly extensively on these, and I love the concept. The concept is, well, it's kind of like a Rube Goldberg machine. Those of you who are old enough, and I'm probably the only one here who is, remember Rube Goldberg as the guy who designed all these crazy machines where one thing would kick off another, and then a tennis ball would drop down a ramp, and it would hit a shoe that would go kick something else, and the dominoes would fall, and things would spin, and eventually the alarm clock would be clicked on. Okay. Purposeless. But the point was that we can make things do things that lead to other things that lead to other things that lead to other things. And that is the concept behind event-driven architecture. Rube Goldberg. Google it. He's a lot of fun. Event-driven is used widely in real-time processing environments, like credit card transactions and self-service scenarios, like getting to the airport and getting to the kiosk. Those are great environments to use event-driven architecture. Basically, there's no batch. There's no flow of program going. There are some kicking around in the system, but the concept is that when something happens, for example, a customer swipes a credit card, or the temperature in an environment exceeds a certain threshold, or somebody hits a button. When any of those physical things happen in the real world, that kicks off a sequence of events in the data world. And those events are executed, and the result of that execution leads to the next step. And it may be any one of a number of results. So basically, this is a way to crisscross back and forth between the digital world and the real world, getting them to work together in ways they've never worked together before, and also to create ways in which various different digital systems can interact with each other without actually being programmed together or attached to each other in any meaningful way. So that's event-driven architecture. By the way, it's built on top of microservice architecture, right? Best way to use it is to use microservice architecture to build your event-driven structure. So that's event-driven, EDA, and you're seeing more and more adoption of this in the many environments now where people are interfacing more and more with devices instead of other people. As automation rises, event-driven architecture rises with it. Web applications, the applications we use in a browser, have their own application architecture. You'll find that the code used for a web application is very similar to code used for a mobile application. They have the same basic structure, but pretty consistently they run in a browser, which is great. Right now, they don't run in all browsers. They run in some browsers, but there is movement at every given moment toward the day when everybody's browsers will run every imaginable application. So it defines the components to be used and how they interact with each other. And it takes fullest possible advantage of the distributed nature of the internet. That is to say, there are various things that various sites can do. And so a web application can simply reach out to those sites and grab use of that particular resource by simply using its universal resource locator, which you know better as a URL. We all use URLs daily when we put an address into our browsers. Well, your software can do the same thing. Reach out for a specific service wherever it may exist on the internet to pull it in and use it for its own purposes. As browsers get better, web applications get better. So you'll find that people who write web applications are constantly monitoring what's happening in the browser world. And as these improvements emerge, they're taking fullest possible advantage of them. The better ones are already working on all browsers. Some of them can even switch to a disconnected mode where they can perform function that the user can use them even when they're not connected to the internet. They buffer all the results and then just simply sync up when they resume their connection to the internet. So this whole concept, if you look back in history, really began with Bill Gates of all people. Bill Gates talked decades ago about the concept of web parts, that there are things happening somewhere in the World Wide Web that you may need. So, for example, I think one of his examples was you're in an airplane and you need to know what the temperature is outside the airplane. I don't know where he came up with that or why you'd want to know that, but you might want to know that. You can easily call up a program that reaches out to the weather service and reaches out to the airplane itself and gets sensor readings and combines everything that it pulls in and gives you a result that tells you just how quickly you'd freeze if you tried to step outside the airplane. But web parts have many, many applications. And basically it says you don't have to write all this code. You don't have to create each and every one of these services or functions. They're out there. You can call them, and you can make use of them. Usually, obviously, these URLs we're using specify where the program can pick up the services that it needs. Similarly, I mentioned it a moment ago, mobile applications also have a fairly unique structure, similar to web architecture. So if you're doing one, you can probably do the other. They, though, take advantage of all of the processing capability, the memory and storage that are in the mobile device itself, whereas web applications only consider what the browser can access. So they're looking at the capacity of the device and whether or not they can do more or less based on the capacities within the device. And again, you want them to be viable on any kind of mobile device. Excuse me. Yes, we're coming to a time where there are really emerging only two platforms that are truly popular, but there are a bunch of other candidates. And at any given moment in time, something could suddenly burst on the scene the way Zoom did during the pandemic. All of a sudden, with all these other video conferencing capabilities out there, Zoom, relatively unknown, became the darling platform for everybody to keep in touch with each other. People are still studying how that happened. The same thing could happen with another mobile operating system. So let's keep that in mind. But indeed, I recently got word that a mobile version was available for a service that I use regularly. Unfortunately, it was only available on the platform that I don't use. So I still have to wait for it to come to my platform. That's pretty frustrating. Another architecture that's really gaining in popularity that basically takes all of the things we've talked about and takes them to their ultimate conclusion is serverless architecture. It is definitely an evolution of the concept of microservices. Okay, basically what it says is there are no servers involved. The user organization doesn't access any servers. They don't buy any servers. They don't subscribe for any virtual machines. They simply access various different services from different third-party clouds. And these run inside software containers. This scales very well for the same reason that cloud scales very well. You need more, you simply request it, and it's provided. You don't have to order more machines. You don't have to subscribe to more virtual machines. You simply say, I'm adding 50 users. I'm adding 5,000 users. And you get the resources that you need to get that done, which means that these things can be spun up and shut down very quickly. If you hire an organization to do something for you that's seasonal, and at the end of that season you just want to shut that down, serverless is a great way to go. It's very flexible and under extremely strong control. It's also one of the least expensive ways to deploy software because servers are expensive and very expensive to maintain. Even virtual machine instances have become relatively expensive. Whereas when you're using none of that and simply accessing services, you may find that those subscriptions, when taken all together, are costing you way less. Personally, I expect to see serverless architecture continue to grow for the same reason that we're seeing software as a service grow. SaaS is becoming more popular than infrastructure as a service or platform as a service, mainly because the user has to do less. In platform as a service, the user does all of the code development, and then they test it, and they compile it, and they load it, and they enable it, and integrate it, and they give users their interfaces. That's a lot of work. And infrastructure as a service, they're still loading up their virtual machines, configuring them, enabling the software on them, loading up the executable. It's a lot of work. With software as a service, you log in and work. Your organization doesn't have to maintain anything. And I think we're moving closer and closer to a time where that becomes prevalent because it's so preferable to having to still do all of that IT work that most companies never wanted to do in the first place. So I think serverless architecture is going to become a primary architecture, if not the primary architecture, over the next decade or so. Okay, before we completely leave the different architectures that we've been discussing, there is one more definition that I want to warn you about. You've probably heard it thrown around in magazine articles, amongst IT professionals, in various different environments. That phrase is technical debt, getting yourself into technical debt. What does that mean? You didn't pay for your computer? No, it doesn't mean that. What it means is that at any given moment, the needs of your organization may be so compelling, so immediate, that you take shortcuts, you do what you can to get a minimally viable product out to them that they can use. This is called the MVP. And I apologize to all the Microsoft MVPs. We're not casting aspersions with that. But the minimum viable product is an important concept because very often developers are called upon to just slap something together so we can get this thing done. And unfortunately, there's all kinds of problems with it, and they have to be repaired someday. Someday will probably come at the worst possible time, thanks to our friend Murphy. So when you choose speed over code quality, you're basically incurring technical debt that you will have to repay someday, and probably at the worst possible time. Okay, having defined technical debt, we finally can talk about some of our best practices. This is difficult in a presentation like this because we're not talking about one given architecture. It would be great if we could do a best practices in microservices architecture. That would be fantastic. We could get into much more detail. But the best practices I'm talking about here are very general. They apply to a number of the different architectures, maybe all of them in some cases. So please bear with me for that. All right, here's the second one. We've already seen the first selection. The first one really is to define clear architecture objectives. What do you want this software to do? What is this application designed for? What's the environment it's going to be in look like? What does that environment need? And so we need to get a functional specification, as we do with any software, specifying everything we want this software to accomplish. Even at this early moment, we want to make sure that we are documenting everything. Most problems that an IT department faces, it faces because of a lack of adequate documentation. The people who are currently maintaining it may not be the same people who originally developed it or installed it, and therefore institutional intelligence isn't going to help. No, but if you have documentation that's well constructed and comprehensive, you're saved harmless, because those new people can consult what the old people wanted them to know. And now we're going to start to choose the appropriate architecture pattern for this application, for the functional specification of this application, for what we really want it to do. So based on the requirements, we're going to choose which model we want to use to develop it. And it may be more than one. We may have a lot of microservices architecture with some portions of it being event-driven. Next, consistently make use of design patterns. There are many different design patterns that have been cultivated by developers over the years. And they're all published and all available to you. They're basically frameworks to show you how to approach different things you want to accomplish within your software. This should reduce your development time, because part of the code is written for you. And also because they're consistent and everybody's using them, including the other teams working on the software you're working on, they increase the scalability and the reusability of your software. Scalability, I think everybody understands. When the organization gets bigger, the software has to adapt to accommodate the greater number of users. Similarly, reusability means we've written this piece of code for this particular function. However, we have other functions that we're developing later on. We can just take this piece of code and copy and paste it into there, and then make minor adjustments, and it'll do what it needs to do there too. There are many of those. There are many times in which a piece of code you developed or a piece of code you've used from a library can be used in multiple instances throughout your program development. Keep an eye toward reusability. It saves you a tremendous amount of time and contributes a tremendous amount of consistency across your software. Because we're working in teams and we don't want everybody working on everything, we want to follow a modular approach. Everybody working on a given module, that they know the interfaces between them, and they write or they develop specific to those interfaces. This breaks the whole process down. You know, whenever you have a big problem, the first thing you want to do is break it down into smaller pieces. This is that model applied to software. And it works incredibly, incredibly well and popularly adopted. Any design architecture you're going to use has to be flexible and also has to be extensible. That is to say, it's not enough to just be able to grow the thing to the number of users. You also may want to add functionality, things that it didn't do before that you want it now to do in conjunction with everything else it does. So you need to be able to extend the capability, extend the functionality of your software as you're going. Okay, in the bullet I say keep scalability in mind when designing. Keep scalability in mind, keep reusability in mind. It's very important that you keep extensibility in mind. These are design ethics, if you will, and they should all drive the way in which you develop your code. It may, in some instances, take you a little longer to do something that will leave you better prepared for future scalability or future extensibility needs. It's worth the extra steps. because when you are called upon later on, the time you spent will be saved multiple times over. So keep them all in mind as you're developing your code. And generally, across the board, as we said before, the people who actually develop code, at some given point, may leave the organization, may retire, may hit the lottery. You never know when people are going to leave an organization. So you want to keep your code base clean. You want to keep it organized. You want to make sure that it's well documented, and somebody who's going to maintain it later on can follow what was attempted here, what the original developer wanted to do. And here's those, they used coding standards. They obeyed, standard coding guidelines. This is normal stuff. You don't want to do any gymnastics, okay? I know that there are many developers out there who pride themselves on their development gymnastics. I think back way long ago, I was one of them. But when you're working in teams, it's all about the team. There is no I in team. Okay. I can't emphasize enough to develop your architecture with security in mind. From the very beginning, security has to be foremost in your mind. If you think back to that 5-layer model we looked at earlier, you may remember that security wasn't mentioned in there. Similarly, when I give presentations on the ISO OSI model, which has 7 layers, people constantly come back to me and say, well, you got session, you got transport, you got all that good stuff, but where's the security layer? And my answer to them is yes, because security exists at every layer. It is baked in. And because that forms a chain of security, that chain is only as strong as its weakest link. Therefore, you have to pay the same level of attention to security at every layer in your software application architecture. Also, I wish I could tell you that you're never going to have a problem. There's never going to be another earthquake, never going to be another hurricane, never going to be another attack. You name it. Disasters happen, and they take out lots of IT provisioning. So we need to be prepared for them. We need to have a good failover strategy. We used to say when we were using tape for backup, hey, the tape backed up, no problem, but will it restore? That's still true today. You still need to make sure by testing periodically that you've got a structure that fails over as often as it's supposed to, and you've tested to make sure that when you need to bring it back, it comes back within your recovery time objective. So disaster recovery planning is crucial as you're developing the application itself, which means you want to use fault-tolerant architectures, architectures that have within themselves built-in redundancies, so that if something goes wrong, there's a contingency that fails it over to another data center, another server, what have you. Crucial to keep developing with architecture foremost in your mind. Again, consistently use the most commonly accepted practices, techniques, and frameworks. They are out there for the purpose of keeping you consistent so that everybody in your organization can pick up where you left off. It is so strongly advised to use some kind of consistent version control system, because you never know when a mistake you made doesn't show up until 2 or 3 iterations later. And then you need to go back to before that version. So now you're going back 4 versions, 5 versions. If you've got a good version control system, you can do that with relative ease. And at that moment, it becomes very important to you to have that kind of facility. Believe me, you don't want to suddenly have to hunt back multiple layers of changes. So use a version control system. And it should go without saying you should use current well-supported technologies. I think the day is over where we all go to the back of our favorite IT magazine and look at the ads there for some fly-by-night software utility that would help us do blah, blah, blah. I think we all understand that brands of software are as important as brands of anything else we use. A dependable, trustworthy brand is immeasurably, worthwhile. Finally, and this may be the most important admonition of all, keep it simple and have fun. Keep it simple. You don't want to add complexity to an already complex environment. You want to keep it simple so that at any given point in time, the software you're developing can be improved, can be repaired, can be resolved, what have you. And the other thing, I wish that I could ask you to give me a show of hands, but seriously, how many of us got into IT because we found it to be fun? And I'll bet you most of you are raising your hands. I know I did. And IT is fun. It's what drives us, and it's what keeps us improving IT all the time. So whatever you're doing as you develop your applications, whichever architecture you choose, have fun with it and develop great products that add to the profitability and success of your company many, many times over. Thank you for your attention today. And with that, John, do we have any questions?
I think we have a couple of questions here. I want to remind everybody that you can type your questions into the Q&A box at any time. We'll do our very best to get to all of them. We're going to start with this question here. Does each architecture have a specific programming language associated with it?
No. Straightforward, no. There are so many more languages now than there are architectures. Some languages lend themselves better to some architectures than others, but I would not say if you're going to use microservices architecture, you must use, Java. No. There's a lot of flexibility in there, and you just have to very carefully match up the application that serves you best with the architecture that serves you best.
Okay. Here's another question. Is there an architecture that supports low-code or no-code development? This should be right up your alley, given your column for application development trends.
Did you tell these people that I write that column? Yes, you may be aware that I write the citizen developer for John. John is my editor, which is why I'm so nice to him.
Must read.
So low-code, no-code is the application development architecture for the rest of us, just like the Macintosh was the personal computer for the rest of us. That is to say that any user should, if they know the workflows within their organization, they should be able to use these point, drag, and click applications to build the software they need to do the job they want to do. That said, each platform, each low-code, no-code platform is graphical. It gives you icons on a field. You can drag those icons around. You can drop them into certain places. You can specify certain behaviors. Very easy, very understandable, very commonsensical, and really, however the platform itself is designed, exists as the architecture for applications designed using that platform. And they vary pretty widely. So when you think about adding citizen developers to your organization, one of the things you may want to do is have them go and do a survey of the most popular low-code, no-code platforms that are out there for them to use. Hint, anybody who's doing low-code, no-code will help your developers immeasurably, because basically they'll run the ball all the way down to maybe the 20-yard line, the opponent's 20-yard line, and then all you've got to do is take it into the red zone. So, take it through the red zone into the end zone. So low-code, no-code is a big boon to software developers. It's going to help you reduce the size of your stack tremendously. So encourage those users to help you.
Okay, we've got a related question. How do you reconcile your recommendation to use source code control and no-code solutions?
Okay, how do I reconcile it? How do I reconcile it? That's an interestingly shaped question. Okay, I think I just answered the question about how do I reconcile low code, no code. It's a very good way, not only for the users to help the developers get further down the field and pick up with a big advantage, a big jump forward, but also it's a great way for those users to communicate the workflow itself and the things they're most concerned about in the workflow to those developers, rather than spending an awful lot of time developing a functional spec. They're basically showing it to them in their graphically developed code. So that's how I reconcile the low code, no code. As far as the source code versioning goes, wow, that's one of those things that I just think by the nature of itself is justifiable. As I said during the presentation, there's a few things that are more painful than having to dig back through layer after layer of updates to figure out. You may have developed 10 or 12 more processes based on a mistake you made a week ago, a month ago, and now all of those processes are going to be impacted by the fact that that was a mistake, and so you're going to have to revisit all of them. That's a big time waste, and I just think that the ability to drop back, it's like system updates when your operating system suddenly develops a glitch, and you can go back to the last version of the operating system before you made the most recent change. You can pretty quickly find out that last piece of software that you implemented on your machine is what's causing the problem. So, I'm not exactly sure what was meant, but I hope I answered it.
Okay, so Ken's asking a question I hear a lot. How does the programming team validate that security is in fact built in at all levels?
Hire security experts. If there's one thing I've heard us all be accused of as technologists, it's that we think because we know technology that we know everything about everything. I think that's an unfair assumption. I think there are a few of us who definitely act that way. But the fact is that even if you're a great software developer, that doesn't mean you're a security expert. There are, however, people who are very, very good. They're truly dyed-in-the-wool, the definition of expert at security. You bring them in to do assessments and penetration testing. Have them try to hack their way in to your application environment. And if they can, they'll tell you how to fix that. But to me, that's the only way that I would ever give final approval to roll out a major piece of software.
Okay, here's a question from Joaquin, who's wondering, in Microsoft architectures, the Microsoft architecture approach, do you recommend one approach over another? My experience with DDD, what is that, design? I can't think what that means. Domain-driven design, that's right. Thanks, Eagle. My experience with domain-driven design works well, and we're very focused, but what's your idea on this?
Well, you've just proven that you're deeper in Microsoft platform designs than I am. I'm really not qualified to discourse on the different various choices, and I think it's really too specific a question. There are certainly people from Microsoft who we can put you in touch with that would be able to talk about that in detail.
So Nalish is asking a question which Actually, a couple of people have I'll kind of mush them together. What will be the impact on existing patterns with the emergence of generative AI and data analytics?
Whose opinion do you want? Okay. So generative AI can write code. Yes, that is true. And I can't tell you that I'm confident that I know an answer to that question. It could go one of many different ways. I think it was Gates. Bill Gates recently released an article where he talked about the current state of generative AI being able to handle basic fundamental functions. That's not a problem. We don't have to worry about that. But there is going to come a point where generative AI develops superintelligence. And at that point, we don't know what's going to happen, right? It could be that we get along really, really well with that and everybody, cooperates. The generative AI becomes part of the development team, probably the most talented part, but let's not even go there. The other possibility is that the world follows the path predicted by the Terminator movies, that Skynet is instructed that its primary task is to protect the planet. And then Skynet, we get to Judgment Day, and Skynet becomes aware. That's what Gates describes as achieving superintelligence. And when Skynet becomes aware, one of the first things it realizes is that the greatest threat to the continued existence of the planet is people. These humans are screwing up the planet worse than anything else. And so it goes about eradicating all the humans, which is a big problem. I joke about it because I don't really want to think about it, but it could go any one of those ways. And it's going to take some time to get there. How much time it's going to take? Everybody's guessing. Nobody really knows. For the short term, I think we're going to find developers doing the same thing that some writers are doing, which is using generative AI to help with their research. Rather than searching item by item, code, keyword by keyword, they simply submit it to generative AI, which looks at everything, brings it all together, and gives you pretty meaningful answers. In some cases, some writers are trying to get the AI to write for them. My problem with that is that when it does that, the AI is reaching out and learning the styles of other writers. So if you want to be a writer whose stuff is published in other people's styles, hey, go for it. Me, I have to hope and believe that my readers like my style. And that's what sets me apart from other writers. And so I'm not using generative AI to do that as long as I live. But it's anybody's guess at this point. It's too new. Of course, it was first described in 1950. Nobody seems to remember. But it's really hit the hockey stick curve in just the last few years. So, use it as a tool, but don't use it as a people replacement because it may do a good job.
So we're just about out of time, but we've had a couple of questions that people want you to clarify your definition of no-code, low-code. I know you did, but maybe just do it again.
Sure, no problem. So there are many, many, many platforms out there in the world that basically present you as a business user. You're not a developer, you're not a programmer, you have very little technical acumen, you can operate a computer. You run this software and it presents you with a palette, if you will, a blank slate that you can add icons to do various different things, to process certain things, to make decisions, what have you. You move these icons around the screen and connect them to each other to match the workflow that you currently do. And when you've got what you currently do translated into these pictures, then it creates software that does that. And for fundamental workflow, you can pretty much do anything you want to do. You can reach out and do intake of 1,000 documents using RPA. You can do assessments of different fields, and you don't have to know what fields are. You don't have to know what the operating code is. You just know that this has to happen. At this point, there's the picture. So that can exist in one of two ways. It can exist as a standalone something that you build and you use, and maybe your organization uses, and that's it. In more cases, however, we're seeing people create functional programs, things that actually will run, and then handing those to their software development team. So instead of saying, okay, start from square one and write me a program that does this, they're saying, okay, I've partially baked this cake, and I'm handing it off to you to finish the baking. So whatever I didn't do or whatever I did clumsily, fix it. And that takes a lot less time than writing it from scratch. That's low code. There's a low amount of code needed. In some cases, there are platforms that require you to code certain things only because the developers were too lazy to figure it out for themselves. But no code works. Low code works. And we're seeing more and more typical business people who have no education in technology, able to translate their business workflow into automation using low-code and no-code techniques.
Looks like that's all the time we have for questions for this session. We're going to take a short break, but we'll be back at the top of the hour for our second session, Modern Application Architecture, Top Do's, Don'ts, and Gotchas, led by the extremely knowledgeable Carlos Rivas, AWS Certified DevOps Professional and popular LinkedIn Learning author. Many, many thanks to Howard M. Cohen for a great session, and to our sponsor, Red Hat, the world's leading provider of enterprise open source solutions, for making it possible. Now would be a great time to check out the extra resources provided by our sponsor. And remember, during our last session, we will be giving away a DJI Mavic Air 2 drone to one lucky attendee, but you must be present to win, so stay tuned. Thanks.
Okay, welcome back, everyone, to our Modern Application Architecture Best Practices Summit, brought to you by the fine folks at Red Hat. I'm David Rammel, editor of Virtualization and Cloud Review, here to moderate the second session on Top Do's, Don'ts, and Gotchas. Our speaker for this session is Carlos Rivas, an AWS Certified DevOps Professional. With a background in software development, Carlos has worked as an independent cloud consultant, helping migrate California community colleges to the cloud. He is currently an AWS instructor, and you can find his work on LinkedIn Learning, Cloud Academy, and Udacity. Carlos, it's great to have you here. Please take it away.
Thank you so much. Always glad to be here and sharing knowledge with the audience. Before we move on from this particular slide, I'd like to point out there's my LinkedIn. So yeah, if you have any questions, I'm more than glad to help. And that's why I became a cloud instructor, essentially to help people, along the way. So if you have any questions, just feel free to reach out. Always glad to help. So with that, let's move on to today's conversation. And we're going to be talking about application architecture in general. So like if you have a problem that you're looking to solve using software development, where do you start, right? The application architecture essentially is your starting point, your foundation. And as you know, it's always good to have a really good foundation so that you don't run into problems down the line. Because we always feel like, we have a problem. We want to tackle the difficult part of the problem, and we neglect security, infrastructure, which database fits the problems best, all those little questions that we just simply forget about. It's always good to have an answer to those as early as possible during your problem resolution. I'm going to touch on containers and DevOps simply because those are really hot topics today, and they're very tightly related to application architecture in general. So I'm going to talk a little bit about that as well. And finally, as usual, if you have any questions, feel free to type them in as we go along, and at the end, we'll take care of those. All right, let's get started. So application architecture. You have a bunch of choices when it comes to where do you start, what do you do. For example, I have this set here, monolithic, that's been around for literal decades and decades, which is essentially where you have your software ready to go in a single package that does absolutely everything. You have microservices, which is essentially a separation of duties between services that make up your entire application. You have serverless, which is essentially another flavor of microservices, but in this case, you're depending on a vendor, and usually a cloud vendor, to provide and manage the infrastructure for you. And event-driven architectures, where you essentially have triggers that respond to particular events, usually a file that comes in, or a user logs in, or something that happens that triggers an application execution. So those are the ones that we're going to be talking about today. So essentially, they are very, very popular. Paying attention to microservices, which is probably the most popular right now. But surprisingly, I've seen monolithic architecture making a comeback. So that's why I decided to include it in this presentation. So let's go ahead and start with that. When talking again about monolithic architecture, you think about the old days when you have a client and a server. You have perhaps a lightweight application on the client side, whether it's a web browser or an actual application. Perhaps you use C#, ASP.NET, or some other client development tool. And then, of course, on the side of the server, you have a single set of modules that you created, and they're all interacting together. There are a few advantages of this architecture, and we'll get to that. But essentially, this creates a very, very heavy server side that has to manage all your clients logging in. So let's talk about some of the positives here. For example, we can say that we can view all data all the time. Essentially, you have a very large application that has visibility into user access, user permissions, user transactions, all that stuff is visible from one location because you have one large application. It reduces network complexity and issues with latency because you're not talking across the network to reach, for example, if you need to access inventory, you just connect to the database and get your inventory. If you need to access whether a user has permissions as an administrator or perhaps a read-only user, you can do that directly from there. It's great in that sense. So if you're running an application that is very point-specific and you feel like you can use this architecture, again, you can reduce a lot of the overhead just by choosing this architecture type. Another thing that I mentioned here is it reduces the number of connections to databases and perhaps to your caching layer. The reason why is it's pretty simple. If you have 10 microservices, there's a good chance that all 10 of them will need to access the same databases or perhaps various databases, increasing network complexity and costs. But if you have a large single application, of course, you reduce the number of database connection and transactions. So again, don't discard monolithic just because it's been around for such a long time. Now, what downsides are using this particular technology? Well, scale is going to be your number one thing. When you have an application that does everything and then you try to scale it to support more users, now you have a problem because when you're scaling everything at the same time. So, you get that flexibility when you're using, say, microservices, for example. If you just want to increase the scale of handling user authorizations and permissions, you can do that because it's a module by itself, right? You cannot do that here. So that's a little gotcha that you got there for this type of architecture. Now, another one is that a small problem can affect the entire application. So if you have let's say that you have a failing module, say an inventory module that's failing, it will most likely crash the entire application because you have all the other application logic within the same architecture. That's a weakness there that you have when you're doing this thing. If you're using microservices, for example, and your user handling fails, that's not going to stop your other applications. So you can concentrate on fixing that problem and know full well that the rest of your application is running healthy. Now, another downside, and I really like this one, is that you cannot modernize your applications because everything is tied in. So this one, it's a really bad one for developers that like to stay on top of technology and advances in general. So let's say that you wanted to use Go language, for example, something slightly more modern than, let's say, you had PHP in the past. Well, if you're in a monolithic architecture, you're kind of tied in there because you are forced to change the whole thing at once if you're going to change the platform or the language, right? If you have a set of independent services, in that case, of course, you can say, well, we're going to leave everything as is, but we're going to take this one module and be able to modernize it. Let's use some of the latest JavaScript libraries. Let's use, Golang or anything like that, and you could do it module by module without incurring the cost of having to refactor your entire application at once. Deployments are harder when it comes to monolithic applications because obviously you're running everything all at once, so you're going to have downtime for sure. You're going to have to shut down your application, do your deployment, perform your post-deployment tests, and then from there you can proceed with your new version. When you have everything broken down into a smaller module, that's when you get a benefit. Well, like now I can do blue-green deployments. Now I can do a rolling update. All those things to avoid or minimize downtime you can do when you have an application that's broken down into components. Now, of course, another one, and this is not too bad, but it needs to be included in here, is that development is harder because you probably are doing version control. If you're whether you're using monolithic or any other architecture, you should be doing version control. And when you have a ton of people, say 5 to 10 developers, all of them working in the same set of files, it can get pretty conflicting, even using version control. So something to keep in mind. So I would say that if you have a monolithic architecture, that's probably going to be for the purpose of a smaller type of application, not something enterprise-wide that's going to be used by hundreds, if not thousands of people. This is more or less what it looks like. You have an application, and the application essentially just connects to a database. There's really if there are modules, so for example, you have here presentation logic, business logic and all, but everything is kind of just baked into a single module, and that just connects to a database. So again, this is kind of like the old way of doing things, but it still works in certain use cases. And by the way, remember that you can still use containers even though you're doing a monolithic type of application. It is still very, very possible to containerize an application like that and deploy it in a modern type of way, using Docker or a cloud flavor of Docker, even perhaps Kubernetes as well. Just know that just because the architecture itself is old, it doesn't mean that you cannot use modern deploying techniques to serve your service. Let's switch gear now, since I'm kind of heavily biased toward microservices because I see this all the time, especially in my line of work. So I'm a little biased into this particular type of architecture, microservices. So what exactly is this? Well, microservices, you have pretty much what I just mentioned, except that if you have particular modules, you turn them into full-blown applications. For example, you would have your user interface, your business logic, your data layer. All those are going to be standalone applications that talk to each other And in that case, you get the benefit of being able to update and maintain those individually. So that's essentially what it is. So don't necessarily associate microservices with containers or Kubernetes or those things. Yes, they go hand in hand, but it doesn't have to be that way. So if you have a more traditional environment out there, just normal VMs, no cloud or something like that, you can still do a microservice architecture just like this. So what are the goods and the bads when it comes to microservices? These are the do's that I recommend. Monitor and measure your service performance, meaning that you want to, just like any other DevOps deployment out there, you want to be able to tell how much CPU are you using, what's the network latency, because now we're broken down into various components. So now we introduce network latency. So one service talking to the other, they may not be in the same computer, they may not be even in the same data center for that matter. So that introduces potential network issues and connectivity. So measuring those as part of your DevOps practice is always a good thing. Now, unit testing and health checks, they're always very, very important, especially health checks, because health checks are what's going to inform your front-end servers, say if you have load balancers or firewalls or perhaps some DNS strategy to point to your services. The only way that they know that your software is actually operating is by querying those health checks and getting a pass or fail response from those. So be sure to consider those when designing for a microservice architecture. Also, remember to set up for recovery and for redundancy as well. So try to make sure that your services can run in multiple copies, because that's going to allow you to scale, but not only to scale, but to be redundant across data center, or as we call it in AWS, availability zones. So when one of those fails for whatever reason, your service can continue to run in another copy in a different data center or availability zone. Now, remember also that this is loosely coupled architecture. So if you can use messaging queues or other mechanisms so that one service doesn't rely 100% on another, that's even better. I know that's not the case for every single thing out there that you can possibly deploy, but just be aware that you should, when possible, say, if you need to communicate, let's say an order to an order microservice needs to talk to a shipping microservice, try to use a messaging queue in between so that, they're not like fully dependent, like, the shipping service is down, so I'm going to fail, I'm going to crash. If you can avoid that crash by sending messages through a messaging queue, then it doesn't matter whether one service or the other is down or is being maintained for deployment reasons, for example. It will still work, provided that you have, that middle mechanism, in this case, a messaging queue between them. And of course, for the sake of simplicity, and this is very, very important when developing microservices, is to define proper boundaries and scope. So try to avoid the whole monolithic thing from the get-go. So if you're going to serve, let's say, user authorization from one microservice, just keep it at that. Just don't try to introduce, well, I'm going to use this microservice for something else as well. No, just try to keep it as simple as possible, right? And that brings me to the negatives, and that's going to be the very first one, actually. Don't overcomplicate it. Just keep it simple, right? If you have a microservice to manage users, just keep it for managing users. Don't start later, adding other functionality in there. Just try to keep it simple. And if you need new functionality, go ahead and create an additional microservice for that new functionality. Never overlook DevOps. That goes back to the monitoring of the positive one. Don't overlook DevOps because, later down the line, you want to understand, like, hey, why is this running slow? When was the last time it was running at a proper performance level? The only way to know those things is by keeping proper metrics along the way. So be sure to measure everything, and when possible, start your development thinking about CI/CD from the get-go and security. One good example of security is to use a tool like a secrets manager or SSM parameter if you're in AWS. Essentially to keep credentials or sensitive information out of your code. You can do things like that. You can start with encryption. You can start with attaching volumes that are encrypted to your application. So those little things that we only think about them when we need them. It's way easier if you know ahead of time, like, hey, this is what I'm going to need for my new microservice. Let me go ahead and just bake it in right now when I'm starting development. And that's why it's good to have this conversation at the architecture phase of your application instead of when you're halfway through your source code for your solution. Ideally, if you can avoid sharing the same database, I know this is not always possible, especially if we're all doing very specific tasks or we're limited in terms of budget and resources. If you can avoid sharing the same database, that prevents the whole point of a single point of failure, because you could face that situation where you have 10 microservices and they're all connected to the same database. The database goes down for whatever reason and you have a significant crash in your production application. So if you can avoid that, that's perfect. Also, since I mentioned messaging queues earlier, I decided to add here the one about avoiding synchronous calls when possible. So when you're calling an additional microservice or perhaps a third-party vendor API, if you can avoid doing a synchronous call, that's even better, because you don't know if that service is going to be down. If you make the call right then and there, now you're in trouble, because now your microservice is going to fail because perhaps a vendor is doing an upgrade or maintenance, and now your code is down for that reason. If you can queue up those calls and have them execute in the background, then your customer will never know, if there was an issue there. You can notify them later that, hey, your order is being processed, or this happened, or we ran into an issue, so there's going to be a delay, things like that. Those are always better than a huge error message across the screen that when people don't know what's going on, right? This is an example of what it looks like when doing this type of architecture. You have some sort of front end that's going to handle the people coming in, whether they're coming to your application using mobile phones or their traditional web browsers. And of course, then behind the scenes, there's going to be a ton of services. In this case, I have account management, inventory services, shipping services. All those things are independent, and they have their own independent databases. So it makes them like really self-contained units that don't really affect the rest of your application should they fail for any reason. This is another example, more or less, of the same, where you have resources using an API front end to call your services. And as I mentioned, they have their own back-end storage, not necessarily separate databases, although, like I said, it's ideal, but they have their own storage and they do their own thing, and then they pass the information back to the calling resource. And then in this case, we're showing an authorization workflow, because once you have a user logged in, you want to know what permissions do they have. Are they an administrator? Are they read-only? And then based on that information, you can, your resource gateway in this case, can do several other things. Let's transition now to serverless architecture. In this case, as I mentioned, this is very, very similar to microservices, except that in this case, you're probably using a third-party vendor to manage and run your code. So I'm an AWS guy, so I'm thinking something like AWS Lambda, for example, is a good example where you have your code running, but you don't manage the infrastructure running that code. You're just worried about your functionality, and that's great, right? You have something like ECS Fargate, which is a containerized version of the same thing. And in that case, it's the same. They manage the infrastructure, and you manage your code. This is more or less what that looks like. You would have an API gateway in AWS. In this case, an API gateway is a service that you can leverage, and you can essentially create an API just by providing the specifications. You don't have to actually do anything. It's already, the infrastructure is managed and provided to you. You just need to provide the actual logic. And in this case, the logic is provided by Lambda functions and individual DynamoDB tables. DynamoDB, if you don't know what that is, it's essentially a NoSQL, NoSQL database, just like MongoDB is as well. It's another very popular option when it comes to those types of storage solutions. And it's very, very ideal for microservices that are specific to one function, which is the ideal use case for Lambda functions. You want them to do a very, very specific task. You don't want it, bouncing around all over the place like, oh, this function will do 3 different things. You never want that. So what are some good things about this particular thing here that we need to consider? As I mentioned, design them for a specific task. You don't want a Lambda function to be, 1,000 lines of logic in there. You want them to be very, very specific. Just input, do your process, and output, and you're done. You want to leverage event triggers, and we're going to get to this when we talk about event-driven. Optimize for performance. Lambdas are very, very expensive in AWS, and they charge you by milliseconds of execution. So you don't want a long-running process. Say, you have something running for 10 minutes, 15 minutes. You don't want any of that stuff. In those cases, perhaps another serverless solution, as I mentioned, ECS Fargate is probably best for your application. So if you're using Lambdas in AWS, my warning to you is to keep the code short and sweet so that it runs relatively fast. And also implement error handling. It's always a good idea to never forget about that, because you're going to have a situation when your code fails and you want to make a decision there whether you need to perform a retry logic, or perhaps wait for a certain timeout delay and then retry, those things. So always good to consider. Never assume that it's just going to work every single time, even though in this case, as I mentioned, you're not managing the infrastructure, but don't assume that everything is just going to be perfect all the time. Now, even though, like I said, you're not managing the infrastructure, but it's never a good idea to ignore the security best practices even in this case. So never hard code values in there that could be sensitive. Use another tool like a parameter store or secrets manager if you're in AWS. Don't forget, you have other technologies, but try to keep it to one thing. So it's kind of bad to be bouncing around, because you're already quite vendor dependent just by using Lambda. So if you make your code depend even more, all of a sudden you are locked into AWS. There's no way to move your code out of AWS ever again. So be careful when trying to leverage 50 different things when using AWS in this case. And as I mentioned, don't run your code for too long, meaning that Lambdas are billing by the millisecond. So if you're going to have a long-running process, perhaps a more traditional VM or EC2 or a container deployment is probably better suited for your task. Also, don't forget the scale. So when you're in the architecture phase, you should expect, have an idea how many users are going to be running your application on a daily basis. And based on that, make a decision, hey, is this good for Lambda? Perhaps I need a 24/7 running process on a traditional server instead of a serverless solution. So those things are very important to consider. Scale early on as soon as possible. And finally, avoid overworking a single function, because that's going to lead to those long-running processes. If you have a single function that is performing 2, 3, 5 different tasks, you don't want that. You want to keep them as simple as possible. This is more or less what that looks like. This is actually, they have a product. AWS has a product that does exactly this very same architecture that you're looking at. It's called AWS Amplify. And what they do is they help you create a front end that goes into an S3 bucket. That will be a static content. And then any logic or programmatic functionality, it will be essentially a Lambda function. And then you have the option, if it's an application that requires authentication, then you can use Amazon Cognito to manage user identities and also user permissions as well. In that case, it's shown here, going to Cognito, getting some permissions, which will give you temporary API keys, and then finally using those API keys to access a DynamoDB's storage. So this entire architecture is baked into that product called AWS Amplify. It's a really great solution for those familiar with web development and JavaScript that want to get into the world of fully serverless application. This is another one, more or less kind of the same, but this one introduces the layer of CloudFront in front of your application to serve as a caching layer for your users, and then, of course, Cognito for user authentication and authorization. And the same thing, in the back end, you have API gateway, you have a ton of Lambda functions. And then for storage, in this case, we're using a more traditional relational database, in this case, Aurora. So you're not locked into using NoSQL type of storage. So if you're not a big fan of storing data in JSON format, and if you prefer more traditional table with primary keys and foreign keys, you have the option of using Aurora serverless as well. So this will still be a fully serverless solution that you don't manage any of the infrastructure. But as I mentioned, as one of my negatives is that in this case, if you do it this way, you're essentially locked into Amazon Web Services for life. There is no escaping. Once you develop an entire application like this, there's no way. It would take humongous effort to be able to move this application, let's say, to Microsoft Azure, for example, if you wanted to do that, because now you're very, very dependent on all of these AWS services. So let's switch gear to event-driven architecture. It's very, very similar to serverless. I try to keep everything kind of tied in together. In this case, essentially, we don't have necessarily something that a user will log in and click a button and something will happen. In this case, when we're talking about event-driven, it's like a file is uploaded somewhere. And you will see that a lot in corporate environments where you have processes that run in the middle of the night, where you have a huge text files with transactions or some other data. And this needs to trigger a process that will manage those files and generate some kind of output. So this is when you would consider an event-driven architecture. So in this case, you have producers, as I mentioned. It could be a storage container where you have you're expecting a file that comes in at certain times, or you have a messaging queue that receives perhaps an email or a message that comes in from another application. And in those cases, it will go to some kind of event channel. If you're in the cloud, you have EventBridge and AWS, for example. That's a way to receive this type of messages. If you're receiving files, you have S3, and somebody could go in there and upload a file for you. And in all those cases, you have consumers attached to those channels, and those consumers will start processing the information. They will trigger a Lambda function. It will perhaps send a message to an auto-scaling group or containers that will essentially go and take that data and start a significant process. And this is in contrast to what I said about Lambdas. In this case, you can certainly have long-running processes, for example, AWS batch that you can use to process large files over time, right? So what can we do here? Use services that scale, simply because in this case, you're talking about long-running processes or things that, for example, you have a file that's uploaded to you. You don't know if it's 100 kilobytes or 100 gigabytes of data that's coming to you. So you need to be prepared to handle that when it actually occurs. Also remember to identify proper triggers. So whether it's a file upload, perhaps when a file is uploaded, let's say it's uploaded during the day, perhaps you don't want to take action on that file at that time. Perhaps a time-based trigger, like traditional cron or scheduled task, it's probably best if you want to process these files overnight only and never during the day. Also, in this case, is 100% loose couple architecture. In this case, there's no tight coupling, so something will happen, but it will happen when the trigger meets the criteria. It's not, like right then and there, like you send something and you expect the response back right away. So in this case, the use of queues is highly recommended, whether it's a file queue, a messaging queue, or some other mechanism to delay and collect the triggers that are coming in to fire up the process. Also, it's good to design, to have proper design patterns in place. So one good example that I use all the time is to have, let's say that you have a priority queue where you have like large servers processing information all the time, and they're designed for your high priority jobs, and you have a lower cost, slower queue where all the others will go. So in this case, you would need a proper design pattern for this to be able to distribute messages accordingly, depending on the priority of those messages. There's other ways to handle this, of course, but just keep in mind that when you have that option, it's not like one fits everything. So it just really depends on your problem. And finally, remember as a positive to consider your cloud options, right? So you have, let's say that somebody's uploading a file, right? And you want to take action on that file. Well, perhaps, Microsoft Azure is better. Perhaps I'm going to use S3 for this one. So you have certain options here. You're not, in this case, locked in to anything. Like whatever fits the problem best should be your way to go here. Now, what are the negatives in this case? Avoid very complex workflows. It's better to have a bunch of simple ones together, working in tandem, right? I'm a big fan of AWS step functions, which is a workflow for these types of architecture. But trust me when I say it can get very complex very fast, even with just like a handful of tasks. Let's say that you're trying to accomplish 5 things. It can get very complex, so it's just not worth the complexity. So in that case, what I prefer to do is like, okay, I'm just going to do 1 or 2 things on a single workflow, and then if I need to add more, I'm going to add them as standalone event-driven processes. Okay. Also, don't forget observability and metrics. Just because this is not something that you're managing yourself and it's running in the cloud, managed by the cloud, don't forget to keep track of the same things, like, okay, how long is this taking? Do I need an alarm to make sure that the things are where they need to be? All those things, remember to consider them as you go along. Like I said, I understand that most of the times in this case, you're using a vendor or something to implement it. So you say, well, it's their responsibility, it's not mine. But when things do slow down, you want to be able at least to provide some answers and say, like, okay, this is happening and this is why. Perhaps we need a support ticket. Perhaps we need to reconsider the architecture and things like that. So don't forget your metrics as well. Versioning is also very important, especially I just mentioned step functions, which is AWS solution to this particular type of problems, and combined with Event Bridge. They provide you with text files that you can use to create these flows. And don't forget that you need to version this because you may introduce some unnecessary complexity that you may want to roll back in the future. And if you have no way of rolling back, now you have a problem, right? So even this little files is good to have in some kind of CI/CD process using DevOps mechanism. So versioning always helps, right? Also, don't forget your other entry points. This is something that a lot of people forget. You say, okay, I have this file that comes in here and it triggers a process. But then, okay, what about my integration testing? What about my user testing? And all those kind of outside edge cases, you want to be able to trigger your process in some other way than sitting around waiting for a message or waiting for a file to come in. So you want to have, even if it's just just for your own testing, right? You want to have some mechanism to be able to trigger an entry into your process, even if it's just for a little bit of realistic testing, if you will. And finally, this one a lot of people forget is the retry logic. You want to know how many times would you like to retry a failed job. You want to know what's considered a timeout. Is it 10 seconds? Is it 5 minutes? What is considered a timeout when you're done waiting for something to declare it a fail process? So yeah, this is also that's something you need to consider early on in your process. Like what would be a good place to start a retry process, or perhaps handle the failure in a graceful way. This is more or less what that looks like. I mentioned step functions, so here it is. In this case, what we're showing is a DynamoDB data streams, which is going to have records being created, records being deleted, and so on. And those generate events, and those events are going to call your step function, which is essentially your entire workflow. And in that workflow, and here we're showing as 2 and 3 Lambda functions that are being called to act upon that specific data. And then from there, you can trigger other processes. You know, I want this data to be stored in another table, perhaps in a more consolidated and meaningful way. Or I want this to go to a third-party system to manage billing with my own techniques. Or perhaps trigger an AWS batch where we'll take that data and send it over, perhaps convert it from JSON to a more traditional RDS table-based format. So, you know, the sky's the limit in this case, but just know that this thing that we're looking at only runs when, in this case, an event happened, which is something changes in number 1, which is the stream of data. This is a more simplified version. And what we have here is an S3 bucket. And typically, I implemented this myself for a demo one time, where you have an S3 bucket and an image would come in. And this image could be an image of a receipt. And you want that receipt to be converted to meaningful numbers so that you can upload it to an expense tracking system, for example. And you can do it just like with this simple architecture that you're looking at. You could do it in AWS. You could associate a Lambda function with an S3 bucket, and the trigger is a file that's just been uploaded. And when that happens, you can call, for example, right here we're showing Amazon recognition, but I believe the one I used in my implementation was Amazon text tract, which is essentially going to say, okay, you know, give me the file. I want to take a look at the file. And if it's a receipt, you know, that has numbers and totals and those things, I want to be able to extract those values. And then once I have them in numeric format, then I would upload it to a database, perhaps extract the date, and perhaps the vendor as well from the receipt, along with the total. And you could actually create very, very easily an expense tracking system with this very, very simple architecture. Of course, as I mentioned, if you do it this way, you're kind of locked into AWS for good, right? So yeah, but yeah, it works. It's a very, very simple way, and there's no user interface. There's no user interaction. All you need to do is, you know, give me the files, put it in S3, and this thing will run beautifully behind the scenes. So let's talk about containers here. Let's see. For containers, essentially what you have is adding a layer between yourself, the operating system, and the application itself. And in this case, you have application A, B, C, D, and so on. It's kind of suggesting that these are microservices, right? And you have this additional layer, which is Docker in this case. It could be, you know, there's several flavors. You know, you have Kubernetes and all those things these days. But this is kind of what it works. It's essentially an additional hypervisor, if you will, to manage your application architecture. This is more or less what it used to look like. You have the containers right here, sharing resources. In the past, when you have only virtual machines, traditional virtual machines, you have a lot of waste because every single machine needs an operating system, needs a bunch of memory and all the resources, and that was kind of wasteful. So when you run Docker, now everybody's kind of sharing all those resources. Not everything is fully isolated, so it's a way to kind of save all those wasted resources from the past. This is more or less what this looks like, and this is one that I see a lot, and I mean a lot. This is a very, very common architecture these days. Pretty much anywhere you go, you'll find an application that is deployed in this similar fashion, where you have containers and a backend of databases. In this case, you have a caching layer, DynamoDB, and a SQL Server. But yeah, essentially your application is it's in there running in this ECS cluster in the form of containers. Now, let's talk about DevOps and wrap this up pretty soon here. DevOps, essentially, most people boil it down to CI/CD process. I kind of do too, but I feel like there's a lot more to DevOps than just being able to build and deploy it in an automatic fashion. But if you wanted to do that in AWS, there's a bunch of tools right there that you could use. Code commit for your Git compatible repository, code pipeline to create your CI/CD processes, and of course, code build, your generic build tool that you can use for pretty much everything, including software testing, building machine images, and so on. Code pipeline, this is more or less what it looks like. It allows you to create a flow where you can access parameters to inject information such as passwords and things to your deployment process. And yeah, essentially, you can also use code deploy as part of this to be able to perhaps create advanced deployment strategy, such as blue-green deployments. And I use that a lot as well, especially with containers. Code build, that's a really, really good tool. It takes a little bit of a learning curve, to be honest. But yeah, once you got it down, it's really, really good, especially in this case that I'm showing here, is to create a container image and store them in ECR container registry. It's really, really great for that purpose. And finally, I like to talk about GitHub Actions because it's really, really hot these days, especially with GitHub always growing and more popular. Essentially, in this case, you have a text file, and that's the equivalent of the code build script. And you can use this to create jobs, and those are build jobs, deployment jobs, software verification processes. You can pretty much bake everything into a GitHub action. So every time your developers do a code push into your repository, you could trigger this automatically and build your code accordingly. Again, this also has a little bit of a learning curve, but I like to show this slide because this is exactly what I do. I have GitHub Actions that generate containers that get stored in the container registry, and then using another GitHub action that get pushed to ECS Fargate. So you create task definition and create your deployments in general that way. And that's really it. Just have a few key points for you. Just remember to consider all your options. Just because monolithic has been around for decades, you can still consider it if your project is small enough to consider. Also remember to take advantage of cloud offerings. I know that there's so many cloud options out there when it comes to services and vendors and all, but always consider those, perhaps for simplicity and speed of deployment. And always design for scale. So know ahead of time how many users are expected. It's very, very different architecture when you're designing for a dozen users as opposed to hundreds or even thousands of users. And also remember to start your DevOps journey as early as possible in your design process because it's going to save you a ton of headache down the line. So guys, if you have any questions, I am here to help.
Okay, great. Great job on the presentation, Carlos. We do have several questions from the audience. But first, I'd like to remind the audience that we can take questions up until about 5 minutes to the top of the hour in order to give you a short break before the next session. So please send them on in now. And let's get to the Q&A console. Well, we have one here from Priya in the audience. It's not really a question, but it's an observation, Carlos. Back when you were talking about the need to avoid synchronous calls if possible. And Priya weighed in with caching will help with that. Do you have anything to say about that?
Absolutely. Yeah. Caching always helps in terms of keeping things moving because it's very, very costly in terms of milliseconds. So when it comes to transacting with a database, I actually measure it. I remember measuring this. For example, querying an Oracle database from your code, it could take up to 100 milliseconds or more, depending on the complexity of what you're doing. And it would be like 10 times faster if you do it through a caching layer because the data is already there and there's no need to do any retrieval from storage. It's like kind of in-memory storage. So depending on what you're doing, especially if it's read-only type operations, yes, caching layer always helps.
Okay, great. Here's a question from Nilesh in the audience. He says, what's your view on the use of various service mesh tools? Like what patterns does it use underlying proxy/sidecar, and such products implementation, configuration looks time-consuming process?
I think I mentioned something like this when I was talking about microservices. Especially if you're introducing sidecars and that kind of things, the complexity can increase more and more. So that's why I say, hey, if monolithic architecture has been around for so many years, why not consider it for any particular project? Because yes, you can have all kinds of advanced failure management and redundancy, and everything is perfect, but it comes at a cost, and that cost is going to be developer hours, whether it's the initial development or the maintenance. So you need people that are really up to date with the resume to be able to manage, all these crazy architectures, especially when it comes to Dockers and deployment and task definition and clusters and all that stuff, especially when you, like I said, you introduce several containers that need to talk to one another all the time. So now you introduce sidecars, service discovery, and all kinds of complexities there. So yes, that's why I mentioned consider the old architecture as much as possible when the application is simple enough. If this complexity needs to be there, well, that's what it is. It's going to be a part of the cost.
Okay, let's try and squeeze in one more question. This comes from Scott in the audience. Any suggestions on choosing the right service bus?
Let's see. Well, it usually the way I like to see it is how much traffic am I expecting? What kind of level of transaction am I going to be seeing here? And then working my way back from there. How big are the messages? If you're going to be moving simple messages, can I do it with a simple messaging queue? You have RabbitMQ, you have SQS in Amazon, for example. You have all kinds of things all over the place, depending on the cloud vendor that you're using, or as I mentioned, RabbitMQ, if you're doing it locally outside of the cloud. So you have absolutely a ton of options there. But yeah, my answer to you is measure the volume and how much time between transactions. If you're going to be running high speed, high transactions, that's going to be your thing right there to choose the appropriate service bus.
Okay, one last question. Should I use mostly cloud native services, microservices, or a combination of both?
I would say a combination of both, depending on what's needed to complete the task. But essentially, don't be afraid to use a certain service from a cloud because I don't want to be locked into this particular vendor. Yes, there's always a risk, but it only becomes risky if you use like 10 different services from the same vendor, and then now you're really locked in for good. But yeah, if you have a combination, you have that flexibility that you could migrate to a different technology if needed down the line.
That makes sense. Well, it looks like that's all the questions we have time for. So thanks again, Carlos, for a great presentation and answering all those questions.
My pleasure. Always glad to be here.